All right, in this video we're going to talk about two more applications to integrals. The first one is finding the center of mass, or the centroid, of a two-dimensional object. The second one, we're going to look at hydrostatic pressure, but let's just look at the center of mass for right now. So what this is, it's an XY point. So the center of mass, or the centroid, is an XY point of a 2D object, where if you think of balancing this 2D object, so I don't know, here's a random looking object, and if we wanted to figure out where we could, say, balance this object on a pencil so that it wouldn't just slide off, maybe that point might be, I don't know, like right in there or something, where we could put a pencil, we could put that almost like a piece of paper in that shape on that pencil at that point, and it wouldn't fall off. So that's the center of mass. So we need to find this X point and this Y point, and a lot of times they're notated with bars. So we just say that the X bar is the X point of the center of mass, and the Y bar is the Y point of the center of mass. Now there's some equations for these X bar and Y bars. The X bar, the equation is 1 over A, where A is the area. A is the area of the object. And remember that you can either use formulas for areas. So like our example is going to be a triangle, and we know 1/2 base times height for an area of a triangle. Or you could use integrals. Area between curves, to find the area. Okay, so A is the area. So the X bar, the X point of the centroid, is 1 over A times the integral from A to B of X multiplied by a function of X dx. And the Y bar is 1 over A, integral from A to B of 1/2 times the function squared dx. Okay, let's do an example now. So let's find the centroid of a right triangle. Right triangle with a base of 5 and a height of 8. All right, so if we look at this, here's a triangle, right triangle, base of 5, height of 8. If we were to estimate where that centroid would be, because there's kind of more area on the lower part of this, I would probably estimate it to be, I don't know, it's going to be somewhere in there. Right, but let's calculate it exactly. Okay, so, first we need area. So area is 1/2 the base times the height. So 1/2 5 times 8, and 2 goes into 8 4 times 5, so area looks like it's 20. All right, so the X bar was 1 over the area, so 1 over 20, integral from A to B, and notice that that was with x's. Our function was with x's. So we've got to look at our x values here. X starts at 0, ends at 5. So from 0 to 5 of x times a function of x. So function of x, well, the only function of x that we could get would be looking at this line. So if we look at that line right there, that line would be, let's see, it's got a negative slope of 8/5. So that's negative 8/5 x, and it starts at 8. So I'm kind of thinking of drawing an axis system on this. Okay, so that's the equation of that line, and that's what I'm going to use for my f of x. Negative 8/5 x plus 8. So let's see, I'm going to factor out an 8. 8/20, because I've got an 8 in both of those terms, and I'm going to multiply through by x. So I'd have negative 1/5 x squared plus x, because I factored out the 8. Now I am going to integrate. So I've got 8/20, and the integral of negative 1/5 x squared, so that would be negative x cubed all over 15, 5 times 3, plus integral of x is x squared over 2, and I'm evaluating from 0 to 5. Okay, so I've got 8/20. Well, maybe we should simplify that just a little bit. So let's see, we can divide both of those by 4, so 2/5. All right, so 2/5 times, I'm going to plug in 5, so minus 5 cubed over 15 plus 5 squared over 2. I don't want to cube 5 at the moment, although I know that's 125. You know what? I'm just going to factor out a 5 squared. There's a 5 squared in both of these terms. That sounds easier to me. So I'm going to factor out a 5 squared, so I will get, so I have that 2/5. I'm factoring out the 5 squared, and that leaves me with negative 1/15, 5 over 15. There's another 5 in there. Plus 1/2. So let's see, with the 5 squareds, one of those 5s cancels. So I'm going to end up with 10 times, this is 1/3. So 10 times, let's see, 1/2 minus 1/3 is going to be 1/6, right? Because we'd have to have, this would be 3/6, and this would be 2/6. So 3 minus 2, yep, 1/6. And so it looks like I can divide both of those things by 2, 5/3. Okay, so there is my x value. So what that's saying is that at 5/3, so maybe like right there, that point happens at 5/3 on the x value. Now let's find the y. Okay, so the formula for y bar was 1 over the area, so that's 1 over 20. The area was 20. We're going to integrate, again, it's with respect to x, so 0 to 5. But this time we're going to integrate that function squared. Negative 8/5 x plus 8 squared. Okay, so integrating this, so we've got 1/20. Because the derivative of the inside part is a number, I'm going to divide by that, so I can do a kind of power rule here. So I can take negative 8/5 x plus 8, that'll be raised to the 3, all divided by 3, and then times the derivative of, or divided by the derivative of the inside part, which is negative 8/5. And we're going to evaluate this from 0 to 5. Okay, so let's see. Still have 1/20 out in front. That 3 is the same thing as 3 over 1, and if I divide by it, that's flipping and multiplying, so it would be 1/3. Same with that negative 8/5, I've got to flip it and then multiply by it. Then I can plug in 5 into this term, so 5 divided by 5, that would be negative 8 plus 8, so that's just 0. and then minus, when I plug in 0, just get 8 cubed. Okay, so let's see, does anything cancel nicely as of yet? Yeah, it sure does. So this 5 would go into 24 times. I can cancel 1 of the 8s. So then I would be left with, I've got 1 over 4, I've got 1 over 3, and I've got 8 squared. And let's see, 8 goes into 4 2 times, and I'm left with 16 thirds. And what did I leave off here? I know that's not right. I know that can't happen, because 16 thirds, that's around 5, and that's like way up here. So something is off. I know what I forgot in here. I forgot a 1/2 in the formula. If you look back to the formula, it's 1/2 of the function squared. So I'm going to multiply through by 1/2, by 1/2, by 1/2, by 1/2, and get 8 thirds. Let's see if that makes more sense. So if I divide 8 into 3, that would be kind of 2 and something. And that, yeah, that makes a lot more sense, that point right there would be 8 thirds. Okay, so to find the centroid, there were 2 different things we had to find. We had to find the x value, so the x value where we could like put our pencil and balance this thing, and then we also had to find the y value, and our y value was 8 thirds. And so if we kind of put this piece of paper horizontally and put our pencil right there, it would balance that triangular piece of paper. All right, so next thing we're going to look at is hydrostatic pressure. I'm going to bring up a picture of a dam here. All right, so we're going to look at hydrostatic pressure. And here's a picture of a dam. And what we're going to do is calculate the force or the pressure on this dam. That's our kind of end result. So as far as hydrostatic pressure goes, if you think of a diver below some water, so if you have or some water and you have a diver, he's super happy, that's below the water, the deeper you go, so the further down that you go, the more pressure you feel. And so this is why like your ears will pop. It's why your ears will pop in cars kind of going over mountains, and it has to do with actually the pressure that the air has against you. But water is a little bit more dense, and so that's going to give it more pressure as well. And so the deeper you go, the more water is above you. And so your depth really depends on how much pressure there is. And it's going to be the same thing with this dam. So it depends on the depth, and it also depends on the size of the object. So you could think of it in how big a person is, but really just think of it as kind of any area below water. The bigger the thing is that you're trying to calculate the pressure on, the more pressure it will have just because it has bigger surface area. So the whole idea of calculating this pressure, which by the way is a force, so units in newtons or pounds is going to be our end result here. In order to do this, it's dependent on density. So density of a fluid or air that we're in. So it depends on density. It depends on gravity. We're only going to add gravity in there the same as before if we're in metric units. And again, that's only for this class. Different books have different notations for this, so just be careful with pounds. Sometimes pounds means force, sometimes pounds means mass, and in this class I'm just considering it a unit of force. Okay, so we'll multiply by gravity if we are in metric units, so if we have like kilograms. Then the other thing that matters is area. So area of a horizontal slice. And the other thing that matters is the depth. So then this is all multiplied. Sorry, I'm kind of going off the page here, but these are all multiplied together. So when we find the hydrostatic pressure, that's going to be equal to a density of a fluid, gravity, area of a horizontal slice, and times the depth of that slice. Okay, so that's the whole kind of big picture of this. All right, so as far as this dam goes, by the way, this is a picture of the Roosevelt Dam, which is, I think it's on the Salt River. It's kind of outside of Phoenix. But the reason that I chose this one is you can look at this. It kind of has a triangular area in there. So it has this kind of triangular shape to it. And so we're going to use that. The dam is about 700 feet across, and then it ended up being about 300 feet tall. And I think actually as I was looking into this, I read that they had to actually increase the height of it later on. Not that that's pertinent at all, but I thought that was interesting. And let's say that this dam, it's not quite all the way full. Let's say that it has water to a depth of 250 feet. All right, I'm going to make a new page. I'm going to redraw that triangle so that we can use it. Okay, so I'm redrawing this whole triangle that we had there. 700 across. The triangle is 300. The water level is at 250. And I think that was all of the information we're given. Okay, so, and for the pressure, we're going to add up, so we're going to integrate the density. So density times, and all of these, well, I'll get to units in just a second. Okay, so density, gravity, area, and depth. And so these are all separate pieces that we'll have to think about. Now I would give you the density. The density of water is 62.5 pounds per cubic foot. And all of these measurements, by the way, are all in feet. Okay, so that's the density. Now, because our units are pounds, and I just talked about this, we're not going to multiply by gravity. We are considering pounds to be a unit of force already, and so we don't need to multiply by gravity. All right, now to area. All right, so area of a horizontal cross-section. So I need to make a horizontal cross-section out of this, and I'm going to say it has a length L. So the area of it really is L times how deep it is, and it is just a little tiny distance right here, and I've got to put some units or some axes on this. If I do that, and I'll call this vertical the y-axis and that one the x-axis, then the little tiny depth there, since it's vertical, why not call that dy? All right, so now I need that length in terms of y. Now where I've placed the x-axis now gives me a y distance from the x-axis up to that length. So that's a distance y. So similar triangles with this. would say that L is to 700. So that's kind of a small length is to a big length. As small height, which would be Y, is to a larger height, which is 300 for that whole triangle. So L is going to equal 7/3 of Y. So my area is going to be 7/3 Y dy. And now the depth. So depth. Y was from the positive x-axis up. So the distance from the water down to that slice, so from the water to that slice right there, is going to be 250 minus Y. We take the depth of the water and then subtract off Y, and so this thing is going to be 250 minus Y deep. So depth is 250 minus Y. Now these are changing. These are dependent on Y. The area is dependent on Y. The depth is dependent on Y. And so our pressure is going to change as we move down the dam. And so to get the full hydrostatic pressure on the front of this dam, we're finding the full pressure on all of it, the force on all of it. We've got to add all that up. So we are going to add it by integrating the density, 62.5, times the area, that's 7/3 Y, times the depth, 250 minus Y. And we're going to integrate over the slices of water. And the water starts at 0 and the water ends at 250. So we only integrate the slices of water. It doesn't make any sense to be adding up where there's air against the dam. It would be negligible. Okay, so let's see, 62.5. Since I've got other fractions in here, I'm going to change that to a fraction. So that would be 1/25/2. And I still have 7/3. So that means I'm going to integrate 250y minus y squared from 0 to 250. And so I've got 1/25/2 times 7/3. And when I integrate, I get 250/2 y squared minus y cubed over 3. I've got to evaluate from 0 to 250. So plug in 250 times 7/3. So plug in 250, so I'd get 250 times 250 squared, well that's 250 cubed, over 2, minus 250 cubed, over 2, over 3. And this ends up being a pretty big number here. We actually end up, if you plug it into a calculator, because this is a little bit big to calculate by hand, you end up getting 3.79 times 10 to the 8th. And our units are pounds in this. That's a lot. So what we have now calculated is the force on the dam. It's the force on that triangular shape. It's the force that the water's exerting on that triangular shape. So, and just notice that this was the exact same idea as finding work, where we took a slice. Work was force times distance, so we had to find the force on that slice and then move it. We're not moving anything here. So we're just taking a slice, finding its area, figuring out how deep it is, because the pressure is dependent on how deep it is. and multiplying that area by the depth, and then how dense the fluid is around it. If you had a fluid that was a lot more dense than water, it would have a lot more weight against it, a lot more force pushing against it. Okay, I think that's it for this one.